Mhm. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Series. And I'm super happy to have Chick Woodward with us today. Hey, Chick.
Hey, how you doing today?
It is December 3rd, 2021, as we round out what seems like a long year, 2021. But I am doing very well in Phoenix. Today, we will probably, we started off in the mid 50F this morning. We'll probably get up to 80s or so. So we get a lot of those Canadian snowbirds coming down for the mild winters in Phoenix. And Chick, where are you at?
I'm currently up in Minnesota, and like Phoenix, we're lacking snow this year, so we're a little puzzled about what's going on.
No snow yet, really? Wow. It must be cold though. You still must be.
It's getting colder, but the use of a mug warmer still hasn't come to full bearance.
Oh, very good. Yeah, I don't have one of those, so I don't have any on top either. So I'm just I'm a loser there. That is a pretty awesome background picture. What is that of?
So this is hiking in the Wind Rivers last summer. It's a good getaway. Highly recommend the Wind River Range in Wyoming.
Very cool.
Having lived in Wyoming for 20 years, it's sort of where I go to relax.
Very nice. There's no internet there, I take it.
Absolutely none, and the better for it.
That is an awesome lake, awesome shot. Very cool. So Chick, what do you like to do for research?
Well, I do a variety of things, primarily related to dust. So we do small bodies in the solar system, to dust formation around exploding stars, a lot of target of opportunity sorts of things, because that gets the adrenaline going. And so that's sort of some of the research I do.
Awesome. Very good. And that, speaking of, is going to lead us to this very lovely AJ article. The infrared evolution of dust in V838 Monocerotis. And Chick, take us away.
Well, so I just would like to chat to folks about this research based on V838 MON studies that we're doing. Again, part of the science that I do is target of opportunity science, and we like to look at a lot of eruptive events that come and go. And we've been studying V838 MON for a while, and it's an example of a class of star called a red luminous variable that most likely comes about due to the fact that we have stellar mergers going on in systems. And having studied nova, it's a nova-like eruption where the change in the visible brightness is quite pronounced and then decays over time. And the nice thing about V838 MON, it was subject of a very interesting study by Howard Bond and company with HST, where you could actually see the expanding light echo emanating from the central source. It always reminded me of the time when the folks in Star Wars were inside the asteroid and actually flew inside this and then flew out. And so it's been a fascinating object to study, not only for the light echo, but because it represents sort of an archetype of things that are seen in the local group. And so these red luminous variables are very high luminosity sorts of events at maximum light. V838 MON was emitting about 1 million solar luminosities at the peak. And it's gone through a very interesting evolution over time. I think one of the interesting things about this, it's been studied with ALMA and HST and Spitzer, and now these SOFIA observations, is we're really in a situation that's very dynamic. And that makes the study of these objects so fascinating, because there's a lot of astrophysics that you can study in real time. In 20 years, you can get a very interesting picture of how things might evolve, and then use that information when you're going to study other similar objects and other systems. And in our own galaxy, we know probably about 4 of these sorts of systems. V838 MON is probably the best study. So I think everybody will remember, it was on everybody's postcards, that expanding light echo ring that we talk about. But we were interested in looking at the infrared characteristics of this object, and had looked at it over the course of time and decided, well, it's time to go take a look at this thing with Spitzer and also with Sophia.
Mhm.
And what we really found, and the punchline of the paper really is up in the abstract, that we really saw some exciting changes in the 10 micron spectral region that suggested to us that we're actually witnessing what had been proposed theoretically to be a dust condensation sequence that occurs in oxygen-rich environments. And people like Knuth and Hecht in early 1990s, all the way up to Thielens et al., had described these processes, but to actually catch them in a single object in the course of maybe 2 decades was really a surprise to do. And that's what we think what we're witnessing with these observations.
Cool.
So I think one of the other interesting things about this is Sophia is a very unique platform that allows us in some sense to study what I would call the brighter infrared universe, whereas the pending launch of James Webb Space Telescope will allow us to explore sort of the fainter end of the infrared universe. And an object like V838 MON would be very difficult to study given the current spectral energy distribution that we observe with Webb. And if you really want to understand how dust processing goes on, you need capability in the mid-infrared, and Sophia provides that. So this is why this platform was called upon to study this object. So if we can go to the first figure,
Sure.
If you don't mind.
There we go. Let's blow that up a little bit. A little too much there. Let's try that.
Right. So this essentially shows the spectral energy distribution that we were able to obtain with the forecast instrument. Forecast is a low resolution grading spectrometer. That's a facility instrument, and it has an interesting backstory because the principal investigator who built the instrument, Terry Herder, and I actually shared an office when I was a first-year graduate student. So it's kind of funny, N years later, I'm using Terry's instrument, and we exchanged many stories getting me into the field when I was a young graduate student back in the day.
That was awesome.
So there's 4 spectral bands that are essentially covered, and I'd like to highlight the first 2 pictures, A and B.
Okay.
They're both interesting, and B caused our team quite a consternation because initially we were really puzzled about what the blue dots were, and they represent the observed spectral energy distribution. The red dots are the atmospheric transmission at flight altitude. And we puzzled for a long time because that was totally unexpected. These plots are in wavelength on one axis versus lambda f lambda in the other axis. And nominally, you would expect, some smoothly declining sort of continuum. Here you see quite an undulation.
Yeah.
And we stared at this, and our first response was, oh, something happened in the pipeline.
Okay, sure. I made an error, right?
Right. But nonetheless, these are the data that we observed in 2019. And this led to a rather interesting discussion about how dust forms and is processed in these oxygen-rich environments. And if we go to figure 2, please, I think it's figure 2.
Yes. Give me one sec. Figure 2, we got some of the images.
Yeah, these are just some of the images. We also obtained some broadband photometric imagery. And at the spatial resolution of the forecast cameras, essentially we were using these for photometry points, but they're actually important in understanding what the spectral energy distribution is. Yes. And so what we did is we pieced together those SEDs, puzzled about them for a while. One of the first things we did is because the short wavelength spectral energy distribution between 5 and about 6 microns actually looked like it had some features that appeared to be like emission lines in them, we subtracted the continuum to try to understand what those were. And that's in the next figure, figure 3,
Mm-hmm.
which is actually an interesting little figure. We've subtracted the continuum to look to see what sort of residuals might be there. And there's a couple of interesting, perhaps statistically significant features that are there. The blue dots represent the observed spectrum with the continuum subtracted. And those particular features in other objects like this have been associated with water vapor emission. That's the 6.3 micron inflection there. And then the other inflection at 6.85 microns has been associated with formaldehyde in objects that have disks. And one of the interesting things that we now know about this particular object subsequent to the publication of this particular paper is high angular resolution ALMA observations combined with interferometric mid-infrared observations really have revealed the presence of a disk in this system.
Cool.
So this was kind of interesting, and it's one of the things that we'd certainly like to follow up on, get some higher dispersion spectra in this particular region to really understand if those are really indicative of water hot bands in formaldehyde in this object. So that was an interesting result out of this particular study. But it's really what happened later when we were puzzling about what we saw in that grading setting between 8 microns and 13 microns that initially had us baffled. And that was that figure 1B up in the corner.
Yeah, let's go back and visit that for a second.
Well, let's go back and visit that one a little bit. That one there, what possibly could cause that shape in the spectral energy distribution? Now, one of the things that you clearly see shortwards of 10 microns is that there's a deep atmospheric absorption there. There is data through that region, but we did a clipping function in the analysis that clip data out below 70% transmission, really to just say we want really high fidelity data. So we thought about this for a little bit, and certainly we have a large international collaborative team on this. And some members of the team had taken some earlier Spitzer spectra of the object when Spitzer was flying. That was the 85 centimeter infrared telescope. That basically about a year and a half ago finally finished its 15-year mission and was shut off by NASA for quite a glorious career of observing the infrared sky. And so it was suggested, let's go back and reassess what the Spitzer observations revealed about the spectral energy distribution in this particular region of the electromagnetic spectrum. So we did that. And if we go to figure 4 now, in the paper. Big 4, there we go. I don't know if you want to cover all 3. So let's go to the top of figure 4. So the top panel in figure 4 represents data taken from the Spitzer archive of what the spectral energy distribution looks like from this object, longwards of 10 microns. And there's 2 different dates plotted there. One date is the 2005 observation, and 3 years later is the 2008 observation. And remember, the eruption of V838 Mon occurred in 2002. So we're sort of looking at 3-year snapshots of this. And just looking at the spectral energy distribution, you can see something's going on. There's been a marked change. Now, the observations of Spitzer actually had data at shorter wavelengths, but they were saturated because it was quite bright. So if we go down to the next panel, we began to think a little bit about this. So let's compare the SOFIA observations taken in 2019 with the Spitzer observations obtained in 2008 that begin to show structure across the 10 micron region. And lo and behold, what you see there is that hump in the 10 to 12 micron region is starting to appear.
Yeah.
in the 2008 Spitzer spectrum, but is much more pronounced
Yep.
in the Sophia spectrum. There's a dip and then a recovery on the red side, and what looks like a very deep dip and recovery on the blue side, although we don't have data points in the Sophia spectrum through that region due to the atmospheric transmission.
Right.
So this was a clue. And the bottom panel in this particular figure shows you what happens if we just kind of focus in on that one Sophia grading setting that covers the 9 to 14 micron region. It's clearly apparent that something is going on. And the emission in this region is usually from different sorts of solid state dust types of material. So this set us thinking, what possibly could be going on? And earlier observations have shown in this particular system the presence of different alumina oxides, water vapor, ALMA has shown silicon dioxide emission. And so all these refractory types of materials are available. And perhaps what we're seeing here is some evolution of the refractory material. And what led us to that conclusion is we've seen this sort of evolution of dust material in the condensing refractory material in nova ejection. As the nova shell goes off, the gas will cool. And once it gets cool enough and falls below the condensation temperature of certain minerals, you start to precipitate this stuff out and the spectral energy distribution changes, reflecting solid state emission features from the grains that you condense. So our thought was, oh, maybe the same process is occurring here. And so how do we go about trying to understand what's going on in this oxygen-rich environment that theoreticians had been thinking about for many decades? You know, what should condense out in terms of the rocky material and how should that go? So that led us to figure 5, which sort of summarizes an initial attempt to try to sort this all out. You know, what is actually changing here? So we took a standard well-oiled model for dust called Dusty and applied it to this particular source, in part because we'd used Dusty earlier on in some other observations of this object back in 2006, 2007. And what we decided to do is look, because alumina was found in the object shortly after outburst, and there was evidence of perhaps silicates being there, to look at what would happen if we varied in a simple model the ratio of the silicon to aluminum.
Right.
And so what this figure is showing you here is an attempt using Dusty models to vary the silicon to aluminum ratio at fixed optical depth. And what you can see is that clearly the models indicated by the yellow line, the green line, the red line, and the cyan line have different shapes to them depending upon the relative mixing ratio, if you will, between those two dust species for a particular grain size distribution. The black dots on the left-hand side of the panel represent some optical photometry that was obtained as part of this project and some infrared photometry that were contemporaneous with the Sophia observation. So that allows us to pin the visible part of the model, and then we see what happens as these models fit the longer wavelength data. And so we first focused on the Spitzer data in 2008. And, you know, one of the conclusions that we said is, well, if we look at this, it's likely dominated by alumina. And that is consistent with what a condensation sequence should be at very hot temperatures in an oxygen-rich environment. And what I mean by hot temperatures is something around 1700 degrees Kelvin. You'd expect that aluminum and oxygen would be the first types of material to condense in that sequence, because aluminum is very reactive in that particular environment. And as you deplete the aluminum, locking it up with the oxygen, aluminum is much less cosmically abundant than silicon. And so you deplete all of that, and then you begin to form the siliceous types of material, right after you deplete it. So, okay, perhaps that's what's going on here. It might be supported by looking at the changes in the spectral energy distribution of the object. So if we roll down a little bit to the next figure, what we're doing here is trying to now take the best model out of the ones above, and get a best fit. And one of the other things we have to do here is also, because of the long wavelength slope of the SED, introduce a second component, a cooler dust component of the order of about 170 degrees Kelvin. Then, the green line sort of matches, the first order. Being an astronomer, we can kind of do that order of magnitude. And we admit the model is not extremely sophisticated, but it gives us a clue as to what's going on, especially when we apply the same technique to the SOFIA data. Now, this panel here is a reasonable representation of the Spitzer data in 2008, 6 years after the eruption, where the silicon to alumina ratio is 2 to 8, essentially 0.2 to 0.8 for a unity model. So then we fast forward to 10 years later, a decade later, when we happen to be fortunate enough to convince ATAC to give us some time to look at this object with SOFIA. So that's figure 6.
Just getting right there. There we go. Wow. Very cool.
So figure 6, then applying the same sort of argument here, let's see what is a reasonable representation of the blue dots, which represent the observed spectra. Now, the forecast spectra are not contiguous because of the way that the instrument works. So there are spectral gaps between here. And one of the things that we like to look at is when you're calibrating different segments of a grading spectrometer, do you get the calibration correct? And that's what those orange dots, help us determine. The orange dots are photometries, synthetic photometry apertures over the image that cover the same spatial area as the extraction apertures used in the pipeline to extract the forecast two-dimensional spectra and then calibrate it. So you can see you get a pretty reasonable match to the spectral energy distributions, and this assures us that the splicing of the different segments is reasonable. There's not some great offset that would skew the results. So again, we ran a series of dusty models, and the one that seems to work the best, adding a third cooler component that was required to keep the spectral energy distribution high from 20 microns to 35 microns, is one where the silicate to alumina ratio changed. Now it's at least 50-50. That gives us a fairly reasonable integrated fit to the observed SED, which is represented in the green line. So we stopped there and said, this is interesting, because I think to first order, we can make a very strong argument that we've gone from an alumina-rich dominated circumstellar environment or dust environment to one now where we're seeing the rise of the silicate species. And that is commensurate with these condensation sequences that people have posited, where you go from alumina through things like augite down to spinel to anthracite as you move downwards from aluminum dominated refractories into refractories that are siliceous.
Cool.
In the dust sense.
Mhm. Yeah,
That's always a tough one to make an adverb out of. And so I think, one of the conclusions that we found is that initially on, we had a dust environment that was dominated by alumina. And now what we're seeing is the evolution of the dust environment and the rise of the silicates, if you will. And this is very interesting because this happened in 20 years in a single object.
Yeah.
And it's probably one of the rare times where we've actually been able to observe this, if not by happenstance, if by just careful synoptic study. And I think this is one thing that is often overlooked in astrophysics, is the information that you can get from the synoptic study of variable sources. It often surprises you. And so clearly, I think what these two figures represent is that there is a temporal change in the 10 micron feature, especially, that suggests that the relative strengths of the silicate and aluminum components of the dust that condensed as part of this merger event has been changing in some fashion. And there's certainly ample evidence to speculate about how these changes happened. It's likely a fairly rare validation of some proposed mineralogical sequences in an oxygen-rich environment that, as far as we could tell, searching the literature, has perhaps only been seen in one other object that was, studied somewhat synoptically, and that's for V4332 Sagittarius, another variable star. So we sort of, discussed what this actually means. And if you go on to page 8, left column top, so slide down a little bit.
Page 8.
Sorry, up one more.
Yeah, 7.
That page there. Yeah, that page. Yeah, we sort of talked a little bit about what the interpretation is of these findings. First, there was a significant amount of aluminum that was responsible for the 10 micron feature when this first developed. And we have some estimate of what that ratio might be, dominated by alumina. And then what occurred is the silicate population, dust population, as a fraction of the total dust that we're observing in the spectral energy distribution models, changed. It increased by 30%.
Yes.
And the increase of silicates with time at the expense of aluminum, follows some models that have been talked about in the literature for a long time. And this is likely what one expects if you interpret the theoretical condensation sequences properly. It implies that initially you preferentially form aluminum oxygen bonds at the expense of silicon oxygen bonds. And then over time, as you begin to form chaotic silicates and the temperature decreases and you use up all the aluminum atoms that become oxidized, you get a higher abundance of silicates showing up. And that will make a 9.7 micron band associated with a silicon oxide band dominate. And that's likely perhaps what we're seeing in that region, that you have a deep dip in the red side, the blue side, near 10 microns, where we fall in the atmospheric transmission. It would be absolutely lovely if we were be able to fly at 80,000 feet.
Right.
To get those last data points, because that would be a very key feature to fit. But nonetheless, I think it satisfies, these observations help satisfy the role that aluminum oxides play in the formation of dust, what the non-equilibrium chemistry is as far as dust nucleation species go. And it's a fascinating example to study dust changes in real time. And it gives us hope that other objects of this type, especially the luminous red variables that are quite bright, you can see them in the local group. Actually, you might be able to study the dust chemistry in some of these objects with Webb.
Very cool. Very cool.
So that's, where we stand with this particular object right now. From my point of view, this is what makes astronomy so fun, because there are objects that you can dynamically study in the course of one's career, which is, it's a good adrenaline rush. Yeah.
That is. That it is. Very cool. Very nice. Awesome work.
Yeah.
Chick, I want to thank you so much for walking us through your very lovely article on B83 Mon.
Well, you're welcome.
And you touched on it a little bit there at the end. So let me probe that a little bit on where we go over, let's say, the next 5 years as both as your research and perhaps as a community. You touched a little bit on JWST. Are there other observatories that can get into that wavelength range? It'll be coming on in the future. Are there other luminous red variables that we can apply this to? And most important, since we only had to wait about 10, 11 years before we saw some significant evolution in the alumina to silica, do we have to wait another 12 years, or can we get the next phase in evolution in, let's say, 6 years or 5 years or something like that?
Well, let me start with the latter.
And I know that's a lot to unpack.
It's exciting. Certainly this particular object warrants further investigation.
Mm-hmm.
It'll be about 6 years since the last observations have been made in 2019. And given the observed evolution of the dust chemistry in this object, you would expect further changes. So I think, certainly our group is very interested in obtaining additional observations of this object. Of course, you always run into the interesting problem with tax. You've looked at this object once before.
Yeah, what's new?
What else are you going to learn?
Well, let me tell you.
Right? And we've learned from the decadal survey that time domain science is actually key to unlocking many secrets of the universe. And here is a prime example of a nuance of time domain astronomy.
That's right.
Now, I mentioned earlier that objects like these luminous red variables, especially galactic ones, can have quite spectacular outburst luminosities when they erupt from the merger. And this is why you need complementary facilities. You need facilities that can study the brighter universe, which is it's a forte of Sophia, and you need facilities that can study the fainter part of the universe. And there are some, the short wavelength bands of this particular object just saturate Webb, and even with the shortest n groups. But these serve as archetypes to study these systems in local groups where Webb is quite effective to do. There are other luminous red variables that we'd like to study. Galactically, V1309 SADS is an example of that. And just the luck of the draw and the success of various processes, maybe we'll succeed, because what you would like to do, at least the local analogs, is build up a database of the behavior that then you can use to interpret perhaps a more statistical survey of these objects in the local group. And so I think this is one of the directions that the study of these objects is going in the field. You try to make detailed observations of the ones that are fortuitously close enough to you to build up an expectation of what you might observe with a telescope like Webb, or some of the new types of infrared optical telescopes that have been proposed by the decadal survey for the 30s and 40s.
Okay, cool. And let me go down just another axis a little bit. Do these observations, are they enough to motivate a new generation of models to compare to, right? You're using Dusty, for example, but there might be other ones. It's probably not a spherical cow, so there might be some asymmetries to it. Does accounting for that asymmetry matter in the models, etc.? So go down the model.
Well, living in small towns out in the country, I like spherical cows because they're often easy to milk. But certainly, yes, there are much more sophisticated three-dimensional dust models available to interpret these objects in detail. I think one of the other challenges, and this is being addressed by the folks that are in the lab astrophysics division of the AAS, is
Oh, yes.
really our mineral models aren't complete. We don't have all the optical constants that we really need for astrophysically relevant types of refractory compounds, especially those that have iron-bearing species in them, which could be used to model these sorts of dust grains. And so that is a real puzzle. And one of the other things that we're certainly looking into is the grains themselves. The way that Dusty works is one assumes that you essentially have a solid grain. And we know from the study of solar system objects that the grains are kind of fluffy aggregates.
Right.
That's a real computational challenge to compute fluffy aggregates that you're mixing optical constants, and people do it, but we really need extensive libraries to pull into these three-dimensional models that are now sort of state of the art. So I think there's a lot of advantage for those working in theoretical astrophysics, in laboratory astrophysics, to make these measurements for us and to provide us a really relevant database from the visible part of the electromagnetic spectrum out into the infrared to really satisfy the needs of a lot of these future missions where the spectral resolution is going up, but the spectral resolution of our database is staying flat. This causes a real problem. Yep. Absolutely. A real problem. And so, there's a lot of potential for future growth. And even personally, there's a lot of future potential for my deeper understanding of Python, because a lot of these new routines are all out there in GitHub. And I'm slowly wrestling that alligator.
Very cool. Well, I'm sure you will be very successful at that one. That was very cool. Very nice. So Chuck, I want to thank you once again for walking us through your very lovely article on the future of luminous red variables and friends. So thank you.
Great. Well, thank you very much for having me.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.